Here's another problem which has a counterintuitive solution. Let's call it the boy born on a Sunday problem. We're going to set the stage with a pretty much simpler problem. A man has two children. One of them is a boy. What is the probability that he has two boys? Let's make an assumption that children are born sequentially. There's going to be a firstborn and a secondborn. In all combinatorial problems, all problems to do with counting, you need to carefully define the mathematical object which encodes the thing that you're trying to count. And here we are trying to count birth sequences. There's a firstborn and a secondborn. And each of these, let's call the birth sequence X1, X2. X1 is either a boy or a girl. Now, I know children have many features, their weight and their height and the color of their eyes and all of that, but for the sake of this problem, the only feature that we are recording is their gender. They're either a boy or a girl. So we're ignoring all of the countless other features that children have, and we're just looking at their gender. All possible birth sequences then would be this set here, which I'm going to call X. So we could call that a sample space. Either to a boy, and the first one is a boy and the second is a boy, or the first is a boy and the second is a girl, and so on. And note that in this sequence here, the position in the sequence indicates when the child was born. So here the firstborn was a boy and the secondborn was a boy. Firstborn was a boy, the secondborn was a girl. And for this problem, we've got extra information. One of them is a boy. So that excludes this birth sequence here where they are both girls. So the sample space for this problem now reduces down to the set, which I'll call Y. So there's these three possible birth sequences: boy, 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 girl, or girl, boy. We're looking for an event, a particular event, the event that he has two boys. That is the subset of this sample space, the singleton here with this birth sequence, a boy and then a boy. Firstborn is a boy and the secondborn is a boy. Then the probability is the size, the cardinality of this set over the cardinality of this. So the probability then, if we have no other information about these children, is the number in this event over the total in what we're calling the sample space for this problem, which is 1 out of the 3. Well, that was just to set the stage for the real problem that we want to investigate. A man has two children. One of them is a boy and he's born on a Sunday. What is the probability that he now has two boys? And what, I hear you cry, has the fact that the boy was born on a Sunday got to do with anything? How does that affect things? Well, it's information coming into the problem. And remember from our previous experience with the problem with the 3 boxes, information changes probability. So now we know not only that one of them is a boy, but he was born on one of the days of the week, Sunday in particular. Let's set up some notation to describe this. For integer I, let's have bi to denote that a boy was born on day I. So B1, day 1, that's Sunday. B2, it's a boy born on day 2. And the same for the girl. So here's the setup. Say we have the sequence. We'll call this a birth sequence. Then If we have B2, G4, that indicates this, that the one in the first position here is the firstborn. So we're dealing with sequences, and the position in the sequence reveals when the child was born. So the one in the first component of the sequence was born first, and this one was born second. So B2 in this first position means that there was a firstborn child. It's a boy and is born on day 2 of the week. That's Monday. And here we've got a girl on day 4 of the week and in the second position. So this is the second-born child. Now that we've established suitable notation to describe this problem, let's go about solving it. We've got the information that one of the children is a boy, and furthermore, this boy is born on day 1 of the week, on a Sunday. So we use the notation, say, B1 to denote that it's a boy on day 1, born on day 1, and B and G to just generally denote boy and girl. These are the possible birth sequences. We can have a boy and a girl, or a girl and a boy, or 2 boys. And specifically, say the boy born on a Sunday, boy born on day 1, is the firstborn, and the second-born is a girl. Then there are 7 possibilities for the girl, specifically G1 to G7. So this is here, the firstborn is the boy born on a Sunday, and the second-born is a girl born on day 6, Friday. Now, if we don't want to write them out, if we can have a sort of a generic procedure. The firstborn, that's in position 1, is this boy, and he's born on day 1. That's what the subscript denotes. And the secondborn is a girl, and there are 7 choices for that variable, G1 to G7. A similar analysis reveals that there are 7 of these then. If the boy born on a Sunday is the secondborn, and the sibling is a girl who is the firstborn, then there are 7 choices for G here. So there are 7 of these, and there are 7 of these. Now supposing we've got 2 boys, and in the first instance, say the boy that was referred to as being born on a Sunday is the firstborn, and the second one is a boy. There are 7 choices for this second-born boy, B1 to B7. What if the boy being referred to as being born on a Sunday was the second-born, and the firstborn is also a boy? Then again, there are 7 choices. So this B1, the second one, is fixed, and the first variable B1 to B7. But note, these are the same. So in this one here, B1, the boy being referred to as a boy born on a Sunday, was the firstborn, and the secondborn was also a boy and also born on a Sunday. Whereas this one says the boy being referred to as the boy born on a Sunday was the secondborn, and the firstborn is also a boy and also born on a Sunday. And this birth sequence is represented twice in this whole sequence of 14. So we need to remove this one. It's already been accounted for here. So in fact, there are 7 of these, but only 6 of these that we count. Now let's tot these up. Let's do our calculation. If Y is the set of all possible birth sequences where there is at least 1 boy, and the E is the event that there are 2 boys, then the probability of this event is the number of elements in E over the number of elements in Y. How many in E? Well, there's these 7 plus 6 of them. 7 here, 6 here. How many in total? 7, 7, 7, 6. So the probability is 13 over 27. The probability has now changed. Before, the probability of there being 2 boys, with no other information known about them, is that the probability was 10 over 30. Now, we've got this extra information. He was born on day 1 of the week, born on a Sunday, and the probability changes from 10 over 30 to 13 over 27. All right, if you have understood that, then here's some homework for you. Let's just extend that problem a bit. A man has 2 children, and one of them is a boy born on Sunday morning. So we're not just specifying the day, but the time in the day. Let's split days into morning or AM and PM. So now you've got more specific information. The boy that is born on a Sunday AM. What now is the probability that he has 2 boys? Now chew on that, and I'll post up the solution in a few days.